Welcome to This Explainer. Today, we're diving into something absolutely fundamental. We are unpacking the laws of motion. It's honestly pretty fascinating to trace the journey from our flawed, everyday human intuition to the brilliant mathematical principles that literally dictate every push, pull, and movement in the universe. Here's a quick roadmap of our journey today. We'll start with the illusion of motion, then Galileo's insight on inertia, force, mass, and momentum, action-reaction pairs, the conservation of total momentum, and finally, achieving particle equilibrium. Let's get right into it. Starting with part 1, the illusion of motion, and uncovering Aristotle's big fallacy. So ask yourself, is an external force really required to keep a body in uniform motion? Our everyday intuition absolutely screams yes, right? I mean, if you stop pulling a toy car, it stops. For centuries, this one simple, everyday observation made humanity assume that motion inherently requires a constant push. And this is exactly where human intuition trips us up. It's a fallacy that even the great Aristotle fell for. He firmly believed an external force is always required to keep a body moving. But the invisible culprit that was tricking him, and is still tricking us, is friction. You see, solid friction or viscous drag are always present. Objects don't naturally want to come to a rest, they are actively being pushed against. Which brings us to part 2, Galileo's insight on inertia, a literal paradigm shift. It is just amazing how a purely mental exercise can completely change the world. Galileo was thinking about double-inclined planes, and he realized that if you could somehow entirely eliminate friction, a moving ball would simply travel forever. If you reduce the slope to 0, making it completely horizontal, that ball's journey literally never ceases. And that leads to a massive, groundbreaking realization. Things fundamentally just want to keep doing whatever it is they're already doing. We call this inertia. It's the universe's baseline resistance to change. Unless an external force compels it otherwise, a resting body stays resting, and a moving body keeps moving. This concept directly paved the way for Newton's first law. To picture this on a much grander scale, just imagine a spaceship way out in the deep void of interstellar space. With all its rockets off and no nearby gravitational pulls to worry about, the net external force on it is strictly 0. That ship doesn't slow down, it just keeps floating uniformly in a straight line, coasting infinitely without any effort whatsoever. Moving on to section 3, force, mass, and momentum, the Newtonian codification. Okay, so to really get a grip on force, we've got to talk about momentum first, which is denoted by the letter P. Momentum is the crucial product of a body's mass and its velocity. Intuitively, it takes way more effort to stop a fast, heavy truck than a slow, light car, right? Mass and speed combined dictate the effect of force, which makes momentum the true, overarching measure of motion. You can actually see this play out in the real world when a seasoned cricketer pulls their hands back to catch a super fast ball. Force doesn't just depend on the total change in momentum, it depends heavily on how fast that change happens. By pulling back and extending the time it takes to stop the ball's momentum, the player drastically reduces the painful force hitting their hands. And that hits right at the heart of Newton's second law, force equals mass times acceleration. It mathematically proves that bringing about a faster change in momentum, which means a higher acceleration or deceleration, requires a massively greater applied external force. Let's put some numbers to this math. Think about a tiny bullet. It might have a mass of just 0.04 kilograms, but if you force it to stop within just 60 centimeters of a wooden block, the retardation is massive. That rapid deceleration creates an average resistive force of 270 newtons. It proves that high acceleration hits incredibly hard, totally regardless of how small the mass is. All right, part 4, action, reaction, and pairs, as we unpack the third law. Now, you've definitely heard the phrase, to every action there is an equal and opposite reaction. But honestly, that phrasing tricks a lot of people. Action and reaction are simply just forces. They aren't some delayed cause and effect thing. They happen at the exact same instant. And most importantly, they act on completely different objects. Force is always a mutual interaction between two bodies. You can really see how this pairing works when you picture identical billiard balls bouncing off a rigid wall. The force the wall exerts to bounce the balls back perfectly mirrors the force the balls exert on the wall. They are equal, they are opposite, and they occur on two entirely separate bodies. Next up is section 5,
Conservation of total momentum, the ultimate consequence.
A classic example of this conservation in action is firing a gun. Initially, the gun and the bullet are just at rest, so that's zero momentum. When it's fired, the mutual forces act for the exact same amount of time. And because these forces are perfectly equal and opposite, the forward momentum of the bullet and the backward recoil of the gun perfectly cancel each other out. The total momentum of that isolated system stays exactly at zero.
Finally, we reach Section 6. Achieving particle equilibrium.
It's kind of wild to realize that being in a state of equilibrium doesn't actually mean there are no forces acting on an object. It simply means the net external force is exactly zero. If a bunch of different forces pull or push perfectly in opposite directions, they balance out, leaving the object's acceleration at absolute zero. Whether we're talking about a resting book where gravity is perfectly matching the upward normal force of the table, or a car cruising smoothly at a constant speed where the engine's thrust perfectly balances out the road friction, the visible stillness hides an amazing mathematical balance. The net external force is zero in both of these dynamic scenarios. So I want to leave you with a final thought. If the world around you is moving uniformly, is an active force keeping it going, or is a head in friction just waiting to change its momentum? I really hope this explainer has transformed how you view the physics of our everyday world, leaving you to wonder what unseen forces are perfectly balancing out around you right now. Thanks so much for joining me.